So it is a great pleasure to have Andy Stuart here with us. You may not know it, but we've been trying to get him here. The Center for Optimization and Statistical Learning has a distinguished lecture every year. And this is it, that we coordinated with ESAM. We knew that Neil had invited Andy, and so we joined forces and we have a joint seminar between the two institutions. So Andy has done a lot of great work in many areas, stochastic differential equations, MCMC methods, especially on inverse problems, function spaces, Bayesian perspectives. And now he's interested in machine learning. He got his PhD at Oxford. I think at the time was one of the meccas of numerical analysis. And then he's had positions in, among other places, at Stanford and Warwick, and now he's a Brent professor at Caltech. Welcome, Andy.
Thank you. Thank you very much. Thanks for both entities for inviting me and giving me this opportunity. We all went out of practice in talking publicly during the pandemic, and it's nice to start to gradually get to doing that. So the topic I'm going to talk about is in machine learning, as Jorge said, and is specifically about what I call operator learning. What I mean by that is learning mappings that transform functions into functions. So much of what we think about in modeling problems in physics, biology, social sciences is dominated by calculus. And one of the real triumphs of calculus is that it enables us to describe complicated phenomena pointwise. And over many centuries, we've been able to write down equations and manipulate them, describing the physical world and based on pointwise understanding of the phenomena of interest. But those pointwise phenomena give rise to differential equations, and they define very non-local and non-linear mappings that transform functions into functions. So, for example, if you have differential equations that involve some forcing that depends on time, that forcing that depends on time will be transformed into a time-dependent solution. Or you may have partial differential equations that have coefficients that depend on space. That gets transformed by the equation into another function of space. So although much of our modeling is in terms of pointwise descriptions, because of the triumph of calculus, much of what we actually want from those models are what I call operators that transform signals or spatially dependent functions into other signals or spatially dependent functions. And what I want to discuss today is the role that machine learning might have in representing such transformations, which are called operators. This is a field which is developing. It has the potential to impact science and engineering. Whether or not it will, I don't know. But I think as a community, applied mathematicians are well positioned to help to try and understand and disentangle when these methods might be useful. And that's the goal of my work, and the goal of the talk is to explain some of that work. The work involves, that I'm going to overview, involves multiple collaborators, and I will make these slides available on my webpage after correcting them. I found a few mistakes at the end. I'll make them available on the website, my website, should you wish to follow up on any of these. But I want to highlight a couple of people in particular who I think are central to the development of the mathematical foundations of what I'm going to describe. One of whom is Nick Kavachli, who was my first PhD student at Caltech. He currently works at NVIDIA, and you take the faculty position at NYU in fall of 25. And Sam Lanthaler, who is a postdoc in my group, he did his PhD at ETH. That's two PhDs actually, one at EPFL and one at ETH. These two people, I think, have been fundamental in establishing the mathematical foundations of this field. And I'm lucky enough to work with them and to be able to convey some of the work they've done. I also want to highlight Zhongyi Li, who is on the computational side of this methodology, and he's played a primary role in making methods work on really hard engineering problems in fluid mechanics and solid mechanics. Okay, so what I'm going to do is talk a little bit philosophically about the general concept of algorithms on function space and try and explain why thinking about algorithms in this way is beneficial. And then I will talk specifically about supervised learning for functions. I'm concentrating on supervised learning because it's canonical. But there are many variants on this, but I'm going to stay in this particularly limited, not limited, but canonical, simple version of learning for the purposes of this talk. But one can go beyond it. But I will describe supervised learning for functions, and then that will lead into the idea of neural operators, and I'll explain some of these and how they work. And I will end by highlighting some recent theory that has been developed, especially with Sam Lanthaler. I welcome questions. These events go much better if you interrupt me, so please do interrupt me with questions. Okay, I want to start with a picture which explains philosophy that I have about many problems. So this is the same image. It's taken inside, I think, Reagan Airport in DC. It's the same photograph rendered at different levels of pixelation. And so here is the coarsest, here is slightly finer, here is finer still, and here is a very fine resolution photograph. The way I'd like you to think in this talk is that many of our computations are done on relatively coarse objects of this type. And for these three images here, you can think of them as being, and I will describe this on the next slide, as being vectors. So at each pixel, there's RGB, so there's three numbers. And then there are a certain number of pixels, which increases as I go from here to here to here. As I increase the number of pixels, eventually I can start to think of what I see here in this image as a function, which takes RGB, so that's a vector of dimension 3, takes a value in R3 at every point in this square. So I've transitioned, and this is an important concept for this talk, I've transitioned from things which are high dimensional vectors, the dimension increasing, to thinking in this last image here of it being a function over a continuum. And really, when we think about what a photograph does, it is trying to capture a continuum thing. It takes light information and renders it on something which is a rectangle. And that as we refine pixelation, this gets closer and closer to capturing a continuum limit. So more in pictures, what you saw in those four images, and the way I would like you to think for this talk, is that in the top left, it was a vector of size R3n, 3 because of RGB, and n being 64 squared pixels. And in the top right, I increased the number of pixels, doubling in each direction. So I increased the size of this vector by a factor of 4, and then I increased it by a factor of 4 again. Now, in many areas of scientific computing, traditionally, one thinks in terms of just picking some n and performing operations there. The philosophical point I would like you to think about is that we should think about algorithms here. This is really the thing we're interested in. And if we think about the algorithms here and we do things well here, I'll get into the practicalities of what that means as the talk develops. But if we think about algorithms as acting on functions, then what we find will work well in all of these cases. Whereas conversely, if someone gives you a particular pixelation, you can invest a lot of time in doing computations of that pixelation. You may not necessarily learn anything about how to do a computation on a camera which suddenly resolves by a factor of 4. Okay, so the basic concept of the talk is that many problems are given to us in finite large dimension. And I put the word don't here because the point of this talk is not to think like this. And one can take this finite dimension and compute an algorithm, and design an algorithm that computes on that task. But underlying many problems, not all, but many problems of large dimension, is an underlying continuum picture. And the way I would like us to think in this talk is that given a task that's high dimensional, actually ask what is the infinite dimensional task that you wanted to solve. Think about an algorithm that works in infinite dimensions and then approximate it in finite dimensions. Now, it's important to recognize by doing this, where you end up is somewhere that you could have ended up by taking this perspective, if you thought about it cleverly. My point is, however, that if you think about designing algorithms this way, it's actually a very straightforward way of designing good algorithms that work in finite but large dimension. So this is a way of thinking that I've instantiated in a number of problems. For example, Monte Carlo Markov chain. There are many cases Monte Carlo Markov chain is concerned with sampling a probability distribution, which is defined by solving some form of inverse problem. And that inverse problem in many physical cases is for a function. And so I've developed ways of thinking about Monte Carlo Markov chain by working on the function space, designing algorithms, and then looking at what that tells us about finite dimensional algorithms. And it leads to orders of magnitude speed up in terms of the rate of convergence as a function of dimension. In the talk today, I'm going to adopt the same philosophy, but I'm going to do it in the context of supervised learning. And I'm going to tell you what I mean by supervised learning precisely, so that it's not making an assumption that you know what that means. But before I do this, are there any questions about the way that I'm thinking and that I've laid out in the first section? Okay, so let me define what I mean by supervised learning. And I'm going to talk about supervised learning for operators, but in red is the roots of this subject, which is supervised learning for classification and regression. So I'll also say what I mean by that. So what I'm interested in is determining, this is really approximation theory. I'm interested in determining a function that I'll call psi dagger that takes u into v. Given the only information I'm given is points un, which are distributed according to some probability measure mu, and their image under the function. So in other words, we don't know psi dagger, but we know its action on a number of points, n. This n has a different meaning from the n in the previous slides. This is not related to the discretization and is now the amount of data. So we have a set of samples from the function. And for simplicity, you can think of these as IID, although there are generalizations. And when I say that the talk is specialized to supervised learning, there are many generalizations of this. For example, we may know something about the structure of psi dagger, and one can go beyond this simple setting, or the observations of psi dagger may not be direct. But in this talk, I'll confine my attention entirely to this problem. And let me just start by making the observation that one of the great triumphs of machine learning was to do classification, in which case the UNs are images of digits, and psi dagger is the classification that tells you which of the 10 digits it is. And the work of Lacan on recognizing handwriting and digits is really one of the great success stories that kickstarted people's belief that supervised learning from data could be productive. So this field started often in the case with U being Euclidean space and V being a set of classes, say the 10 digits or the letters, and also regression, where the output space V is also a Euclidean space. But what I want to do is look at the same problem where the inputs and the outputs are themselves functions. So U, the calligraphic U and calligraphic V, are functions. And for simplicity, I'm going to take these functions as being defined on the same domain, D, which is a subset of R little d, and just be real valued functions. But these easily generalize. So I can have different domains for the input and the output functions, and these need not be scalar valued, they can be vector valued. Just to be clean and simple, looking at this problem. So if you want examples to think about, think about the two examples I discussed at the beginning. So imagine a non-autonomous ordinary differential equation that's being forced by some time-dependent forcing function. And one might be interested in transforming the forcing to the output, the solution of the equation. In weather, for example, or climate, you might be interested in the seasonal forcing that comes from the motion of the Earth around the sun and its rotation. And there's also climatological forcing coming from anthropogenic sources. One might be interested in transforming that forcing into the response of the system. So although many physical problems are described in terms of pointwise information, differential equations, what we want out of them is often a transformation of one function into another. And numerical analysis has provided a way of computing that transformation. And what we're going to investigate in the talk today is whether there are alternatives that may be competitive, that take data possibly generated by standard numerical analysis methods and try and replace the standard numerical analysis method by something that is learned from data. Questions? Yes.
Sorry, just really quickly, besides these kind of data-driven approaches, are there other competitive approaches or competing approaches to approximate this kind of function?
Yeah, I mean, I think the standard competing approach is classical numerical methods for solving the differential equations. And I'm not at a point where I want to say that the methods I'm going to describe are going to replace classical numerical methods. Indeed, what I'm describing here will be trained using classical numerical methods, so they're an integral part of it. But it's not nor is it the case yet that it's clear when the methods I will describe will be competitive with classical numerical methods. So I'm developing a research program to try and understand those questions, both through empirical studies and theory. But I think those are the two main competitors, purely data-driven or numerical analysis-based approximations.
Thanks.
Thank you. Okay, on this slide are going to be two loss functions, but they're interchangeable in what I'm going to say. I'm going to describe the training and testing as if I use different loss functions. I don't necessarily do that. I just wanted to show you two types of loss functions. So the question we're now going to address is how do we go about solving this problem? We're going to introduce a parameterized class of functions that map U into V, remembering that U is itself a set of functions, and so is V. So this, what I call parameterized class of functions, are operators. They take this function space into that function space and parameterized by theta, which I view as a subset of Rp. And we would like to choose a value of theta where psi is close to psi dagger. So one way to think about that is to write down a loss function, which looks at the difference between psi dagger and psi, averaged with respect to mu, which was the measure I assumed gave rise to the data, which I'll talk about in a moment. This is called a population loss because at the moment I haven't used the data, I've just averaged with respect to the measure mu. But if I approximate this expectation empirically, that is, I sum this and divide by 1 over n and evaluate at u end, which are independent draws from mu, then I've assumed that I know psi dagger at u end. And so this will be known to me, us. And then once I empirically approximate this, I'll get a function of theta, which can be optimized. And the norm here is the norm in the output space, which is a space of functions. Now, in practice, it turns out that from my empirical experience, our empirical experience is that it's better to work with relative error. And so I've written that here in the testing part of this slide. So I'm conveying two things, that there may be different loss functions that are relevant, and I'm just writing two here. And secondly, I'm distinguishing between training and testing. I will distinguish between training and testing verbally in a moment. But secondly, I wanted to point out that here I've made a change, which is firstly to remove the square root, and secondly, to normalize this so that the error is relative. In our experience on almost all of the partial differential equation-based problems that I will discuss today, it's better to work with relative error. In this part of the problem, in the training and in the testing. But there are exceptions to that, and I don't have a theory for when one is better than the other, but generally being relative is a good idea. The difference between training and testing, so here I will use a data set to approximate this empirically, and I will use a different data set to approximate this empirically to evaluate the algorithm. Any questions? What I'm going to do now is give two examples. These come from the physical sciences, and however, there is no need to understand this talk. You don't need to understand the physics of these problems, but if you do understand the physics of these problems, that's good too. This is called Darcy flow, and it's a simple linear partial differential equation that describes fluid flow with velocity with pressure V, which is in a porous medium. And A is a coefficient which describes the permeability of the medium, relates to the porosity and permeability are different, but this is the permeability and it describes the structure of the medium. So think of flow of water through a dam. And the solution V is best thought of in terms of the pressure, in terms of the fluid. It's a simple partial differential equation. There are generalizations of this, but let's just start with this simple one. It's a linear partial differential equation of V, but the mapping that takes you from A, the coefficient, which varies in space, to V, the solution, which varies in space, is a nonlinear mapping. Okay, so although it's a very simple equation, it defines a mapping on function space from the coefficient to the solution. It's that mapping that I want to find from data. And I also would just want to emphasize two things about that mapping. I've emphasized that it's nonlinear, despite the fact that PDE itself is linear, and the mapping from A to V is nonlinear. But secondly, it's non-local. So that is, the solution V depends on A at every point in the domain. So I want you to remember those two concepts of nonlinearity and non-locality, because when we define generalizations of neural networks to learn mappings of this type, they must necessarily capture both nonlinearity and non-locality. And I'll have something to say about that towards the end of the talk, theoretically. So the typical input examples for these problems are things of this type: piecewise constant functions with complicated interfaces. You can think of this as, for example, being made of quartz and sand, so different types of material. And we construct a probability measure mu by choosing this interface to be a random function. I'm happy to go into details afterwards. But this is very complex. It maps to the solution, which you think of as the pressure, piezometric head, it's sometimes called. This is a much smoother object. So I will have a probability measure on these, and I will have these are inputs, and I have outputs like this. I want to learn this mapping. And it's nonlinear and non-local, meaning that this function depends non-linearly on that function, and every point in this domain, at every point, if I take any point in this domain, it will depend on this input function everywhere. Okay? So although calculus is pointwise, the objects that arise from calculus are very non-local. Now, I talked at the beginning in terms of do's and don'ts in terms of algorithms. And the word don't is associated with a paper that I have very high regard for, so I just want to highlight that. This was early in the application of neural networks to the solution of problems in partial differential equations. And this paper, Zhu and Zabaras, computed at a fixed n, in my notation at the beginning of the slide, the fixed discretization, learned a neural network that learned the mapping I've just described to you. And they obtained an error, this is relative, so they obtained an error of 2% at a given resolution, which was 50. However, if you take that method and try and apply what you've learned at that 50 by 50, if you try and take that method and try and apply it at different levels of resolution because there was nothing intrinsic about the methodology in terms of capturing the continuum limit. Now, as you take what's been learned here and try and apply it elsewhere, the error increases. The methods I'm going to describe, and this comes from a particular version, which was our earliest attempt at this, called PCA-net, have a different property that if you look at the error as a function of resolution, there are three different parameter choices here, but let's just fix one of them. The point here is that the relative test error that we make is more or less independent of the resolution. And that's because we conceive of a method here which makes sense when applied to functions. So if you learn it at one level of resolution, you've actually learned something that makes sense at different levels of resolution, and you can reuse the same weights and biases that you've trained at different levels of resolution and still obtain a good error, here around 3%. Okay, so this summarizes the basic point of the philosophy of the way I'm thinking, is that we're essentially learning something intrinsic about the problem that has meaning in the continuum limit, rather than learning something specific to a specific discretization that doesn't transfer. Yes, I'll get them both. Yes.
Do you ever, I would guess you get multiple mappings, right? Sometimes. And so do you ever think about which mapping is the one I should use?
That's a good question. So in these problems I'm describing, the mapping is uniquely defined. So there is, for every input, there is a unique output. There are interesting problems which we have looked at with a continuum version of transformer architecture, which I won't have in this talk, where we've tried to learn a mapping even though one doesn't exist. And I'd be happy, there are actually in time-dependent problems that might be of interest in the things we talked about this morning. So I'd be happy to discuss in more detail.
And the work at the top,
Yes.
which doesn't work so well for different resolutions, you said you have a high regard for their paper.
Yeah.
What is that?
So the high regard is that they were the first people that I'm aware of to conceptualize the idea of using neural networks to solve, to learn mappings between spaces of functions. They happen to do it at a given resolution, but they really were the first to do it. So I think it's an important paper for that reason. Second example is a 2D incompressible Navier-Stokes equation, a formulated periodic domain formulated in vorticity stream function formulation. This is an equation for the vorticity omega, which is a scalar in this case. And it involves the velocity, it happens to be a non-local function of the vorticity, and that non-local function is described here through the stream function. You don't need to understand the details. Many of you already will, but many of you won't be familiar with this area. That's fine. This is a partial differential equation. The non-locality is not the same issue I was talking about earlier. The non-local function I'm interested in and talked about earlier is the mapping that takes the initial condition of this equation, which is a function defined over the torus, over a unit box with periodic boundary conditions, into the vorticity at a positive time. And in the particular example, we're going to construct initial conditions drawn from a Gaussian measure. So you're all used to Gaussians characterized by covariance. In infinite dimensions, the covariance, instead of being a matrix, is an operator, and here it's an inverse power of the Laplacian shifted by the identity. What we're able to do here is predict the solution of the Navier-Stokes equation in this vorticity stream function formulation from an initial vorticity, and then predicting up here is the simulation by a pseudo-spectral method, and here is a computation formed, learned by a neural network. And yes.
So are you learning it? You're not learning it just from this one input?
No, not from one input. Sorry, I need to be clear. There are tens of thousands of learning typically, that order of magnitude.
Yeah. Okay.
So an important question in this area, that has a cost, obviously. And a natural question is, having learned this map, when is it actually going to be cheaper to evaluate than solving the PDE? So I'm going to tell you something positive about that, but I'm going to qualify it in a moment. But let me just talk about it in terms of the solution of an inverse problem, which is to recover the initial condition of the fluid from an observation at a positive time. So this is the initial condition. This is the solution at a positive time, which is smoother. That represents the smoothing of the Navier-Stokes equation. And the grid there is where we observe this. So we want to recover. This is the solution at, say, time 1. This is the initial vorticity, and we're trying to recover it. At the top, here in the middle, we see the recovery of the initial condition, the mean using Monte Carlo Markov chain. So this is formulated in a Bayesian way. And to the right, you see the same thing where we've replaced the solution of the partial differential equation by a surrogate, which is based on something called the Fourier neural operator, which I will describe. But it's a cheap surrogate. And just to say that in this particular case, I will qualify this in a moment, the use of MCMC requires on the order of 10 to the 4 evaluations to converge. So that means 10 to the 4 evaluations of the solution of the Navier-Stokes equation. And using the original pseudospectral method, which gave rise to the data upon which we trained the Fourier neural operator, this took 12 hours, whereas this took 2 minutes. Okay, that sounds really good. However, it's important to realize that here I've done 10 to the 4 evaluations to run MCMC, but to train this FNO, I actually had to do a similar number of evaluations, smaller, but similar order of magnitude of the number of evaluations of the forward model to train the Fourier neural operator. So although this MCMC and Bayesian inverse problem, there's an enormous speed up. The training cost means that in fact the savings was only a factor of 2, not the order of magnitude that you would see by looking at these two. This highlights an important question, which I think is as yet undetermined, which is related to generalization. If we invest a lot in training a model, which typically involves solving by a classical numerical analysis solver, that will only have been useful to us if we're able to use the model beyond where we trained it, and to do that repeatedly. Then the cost of training becomes amortized, and there's value in doing this. But when it's valuable is open at the moment. Yes.
Are there any symmetries in this problem that you can take advantage of to extend the training data?
That's a good question. Yes, there are, because of the periodicity. We didn't do that, but in general, that is a useful thing to do, and it is done, as you probably know, widely done in image processing, for example. And we have done that in some cases, but not on the specific example. There's translation invariance, for example.
Right.
Continuum.
Yeah.
If I understood, I think your forcing functions were constant.
No, it's a Kolmogorov flow, so which means yes, in this case they are constant in time, but spatially varying. So they are eigenfunctions of the Stokes operator.
Fixed instant. So if you wanted to change the forcing function, you'd have to retrain.
Good question. Yeah, so we have that's exactly right. Yeah, so this operator is trained for a fixed forcing function. However, we have also trained operators which map the initial condition and the forcing function to the solution, and also have done that with time-dependent forcing functions. But you're absolutely right. In this case, it's trained for a fixed forcing function, which is another aspect of that limits the potential value of this in terms of its generalizability. But one way around that is to learn that dependence too. Thanks. Yes.
So what is the accuracy for this numerical solver? I wonder whether the comparison is fair, because for the FNO, it's looks like relatively.
I'll do this question. So that's exactly the question I asked myself, and many people in this field are not asking that question. If I could abstract it, it comes down to the question of, if I look at the cost of running a model for a given error, how does that behave when I compare the classical numerical method with the neural operator? I will show later that the neural operator is able to represent to arbitrary accuracy any operator, just as in this case the pseudospectral method is. Pseudospectral method is absolutely the best way to solve this problem because of the periodicity. And if you combine it with exponential time stepping, that aces the problem, and there is a lot of theory and practical experience that shows that's the best method. And indeed, if you look at the asymptotics of this problem, where you ask for smaller and smaller error, the rate at which the cost increases goes up much more slowly for the pseudospectral method than it does for the neural operator. So if you're interested in asymptotics, this classical numerical method is asymptotically better. That's empirical, but I believe it also to be the case theoretically. However, if you are interested in obtaining a given error at a particular, a given error, say 5%, you can often do that orders of magnitude more quickly with the standard method, than the standard method, orders of magnitude more quickly than the standard method by using a neural operator. But knowing when to do that is also a difficult question. So, and the question you ask is a great one, and it's one of the reasons why the jury is still out as to whether this is a good thing to do. Thank you. Okay, so let me just tell you a little bit about the neural operators and describe a few of them that underlie what I've described to you. I think a useful way to, I'm going to describe three of them. The PCA net, which gave rise to the first picture I showed where I had don't and do, and I had the flat curves and the grower curves. And then I'm going to describe something called DeepONet, which arises from the group of George Kaniadakis in Brown, which generalizes PCA net in the way I will describe it. And then I'll describe the Fourier neural operator, which is more complicated, but looks like a deep neural network. So in that way, it's more simple. The first two fit into this general way of thinking, and much of the analysis that is justified in terms of universal approximation theorems that I'll describe later comes from this picture. So what are we trying to do? We're trying to find or approximate a function psi dagger, which takes U, a space of functions, into V, a space of functions. A useful way to think about doing this is to find an approximate factorization of the identity on the space U and on the space V, which involves passing through a latent space of finite dimension. So what I mean here is that F and G, when composed, G composed with F, should approximately return the identity, and yet one is passing through a latent space of finite dimensions. So a classical way to do this is by principal components analysis. Many of you will have experience with that, and it has an analog on function space. So if you have a probability measure on spaces of functions, U, with a covariance and bounded second moments, you can compute principal components analysis the same way you do in finite dimensions. You form an eigenvalue problem. And principal components analysis, if you think about it the right way, is indeed a approximate factorization of the identity. And I will describe that in a few moments. Do that on the input and the output spaces using data. And DeepONet, which I will describe, generalizes this, but has the same structure. And so again, the composition of G with V, F, will approximate the identity on V. And then you approximate psi dagger by mapping into this latent space with the encoder F, finding a neural network that maps between the latent spaces in the input and output, and then decoding using GV. So first two methods I'm going to describe have that structure, and analysis can be performed to understand neural networks. And Nick Kavatsky, that I mentioned earlier, has developed really beautiful theory that does this in very, very general settings.
Question.
Yes.
Some of your earlier images, the input images look rougher and the output images look smoother.
Yes.
So the U space that probably would require more eigenfunctions to, but do you not need to, you only have to retain the eigenfunctions that influence the output?
That's a very good question. Yes, so that's correct. Yes, so although it would, I'm sorry. Although, let's go back to the example you were mentioning. Although this is very rough, so if you do PCA on this space and on this space, as you rightly point out, the spectrum will decay much more slowly here than here. But on the other hand, the sensitivity of the output space, which is where I'm measuring errors to the details of what happens here, is quite small. And so it is possible And that relates to the dimension of the latent spaces that I described. It's possible, even though the decay is slow here, compared with the decay here, it's possible to get away with a relatively small number of eigenfunctions because you're interested in this output. And we have in the case, it's not in my slides, although it's in the backup slides if you want to discuss it later. We do have theory in the linear case to study that question by using scales of Sobolev spaces to address it. And in that case, you can actually understand rates of convergence and how they depend on the regularity. Okay, so the PCA net is based on doing PCA in the way I've said. There's a lot of notation here, but I would like to take the time to decode it for you. I'm going to take a function u in the input space calligraphic u and match it to a function psi PCA of u, parameterized by theta, which is in the output space calligraphic v. So this is an operator that takes u, which is a function, and gives me psi PCA, which is another function. And here I'm looking at its evaluation at y. This works as follows. I take the PCA basis functions on the output space, and I take a linear combination of them. And that linear combination is going to be a coefficient, which will be a scalar for each j. There are m of these. That relates to the question we've just been discussing about how many, the size of the latent space. Each alpha j is a neural network, and it's parameterized by theta, which we will learn. These coefficients of the basis functions found in the output space have as input the function u, but specifically they have the encoded function u, which is found by mapping the function u onto a finite number of PCA coefficients in the input space. And indeed, it's this specifically we were talking about a couple of minutes ago. How many of those do you need? So there's the dimension of L is taking u into a finite dimensional space. That's the latent space of the input. And M is the latent space of the output. Okay, so that's this involves training at two levels in the sense that the data is used to compute PCA bases in input and output spaces. And then the data is reused to compute the neural networks, the alpha J's, which are coefficients.
Yes. But you also need to specify the probability measure for the input and output bases.
You don't need, I mean, it's implicit in the data. So the assumption is, and the way we do the experiments is to generate, we choose a probability measure. I think I know where you're going. We choose a probability measure and then we sample from it. And, but we don't use any of its analytical structure in the training. But I think what you're getting at now, catching up, is that the choice of that measure is probably, it is very important in terms of how this performs. And the design choice is not something we've worked on yet, but we're developing that program to ask for a given task, how should you design the input? So in some problems in plasticity, we're starting to look at exactly that question, how to design. We have empirical stuff, but trying to be a bit more systematic. Thank you. Okay, DeepONet, which was a fantastic paper, which is one of the first to systematically develop neural operator. And it's based on a paper which actually goes back to 1991 by Chen and Chen, which is the first that I know of that thought of neural networks as mappings between function spaces. Because of the timing, it didn't really go anywhere in terms of applications, but that paper is the first. That had a shallow neural network in it, and DeepONet made it deep and made it work. But in comparison with PCANet, this is not the way they present it, but it's pedagogically a good way to present it. The difference is that rather than prescribing the output space to be the basis functions computed by PCA, these output basis functions are themselves learned. So as well as learning the coefficients and the parameters that give rise to them, one learns these output basis functions. In short, sometimes it's better to learn them, and sometimes it's better to learn them using neural networks, and sometimes it's better to do it with PCA. And I could not give you, that's an empirical observation, I could not give you a theoretical explanation as to when it is better to use one or the other. And again, that's highlighting a general issue in this whole area, which is, this is a new area, and we're trying to develop theory, but we're not at a point where we can answer the kind of questions that are routinely understood for numerical methods in partial differential equations, because that subject is 80 years old in terms of starting with von Neumann and everything it follows from what he said in 1950s. The FNO is a slightly different architecture, and one thing I would like to highlight in both PCANet and DeepONet is that they're what's called linear methods. That doesn't mean they depend linearly on the input. They're linear in the sense of approximation theory, meaning the following: that the set of basis functions in which you represent the output space is fixed and independent of the input. So here it's found by PCA, here it's learned, but it means that there's a limit to how well you can do, which is related to approximation theoretic questions about how well you can approximate an operator in where the output is in a given linear span. Okay, so these form this linear span. And there are problems where there are Kolmogorov barriers, as they're called, to approximation, to basically give lower bounds on accuracy that one can achieve through linear methods. The Fourier neural operator is a nonlinear method in that the output space representation depends on the input. It is best thought of as a generalization of deep neural networks to operators. And you remember that at the beginning I said we have to be nonlinear and non-local. So deep neural networks have been very successful. They are nonlinear, and we're going to inject non-locality into them in the following way. So structure of a deep neural network is, I'm going to come to R and Q in a moment, but it's based on a composition of a pointwise activation function, which is nonlinear, to a linear affine map applied to the input. So in standard finite dimensional neural networks, rather than a function v of x, one has a vector v, apply a matrix to it and shift it by a bias. And then you learn these weights and biases, and the combination of the nonlinear pointwise activation, pointwise on vectors, with these linear, is enough to achieve universal approximation. And indeed, there is some theory about how being deep is more efficient than being wide, and lots of empirical evidence that this works well. If we want to do this on functions so that v is no longer a vector, but rather it takes values in Rd at every point x in the domain, uppercase D, we need to do something non-local. And although we originally introduced this idea with Fourier basis, I want to say it a bit more generally, and you'll see why in a couple of minutes when I get to some theory. I want to decode this for you. But K is a non-local operator, which works on V. And I want to highlight two things. It's non-local because it involves, I'm going to just choose some set of basis functions. And if you like, these can be sines and cosines, and this could be the Fourier case, but they don't have to be. I'm going to take the inner, and there'll be uppercase M of them. I'm going to take the inner product of the function V with each of the basis functions phi M, multiply it by that basis function phi M. So it's just projecting V into space phi M. And then I'm going to have a learned coefficient, gamma M. And you can think of this as being pointwise with respect to M. So in this transform space, which is, you can think of it as Fourier transform onto a finite basis of size M. In this transform space, K is also pointwise. So that means this shares a lot of the advantages of the deep neural network, which is pointwise. But to be non-local, we're combining pointwise in physical space with pointwise in Fourier space. Okay, so this is both nonlinear and non-local. And as I will say in a moment, all three of these methods are universal approximators, meaning that under some conditions, the types of which we'll see in a moment, these operators can approximate wide classes of mappings between function Banach spaces U and V. But I need to tell you one other thing, which is that to make this work, we typically have a lifting and a projection at the beginning and the end. And remember, the input space was functions U from domain D into R. And I'm just lifting that up into from D into R DC, DC being the number of channels. And Q projects back down into the function space that we're interested in. Okay, so this is not a linear approximation method. The output space in which you approximate does depend on the input function U. And it's nonlinear and non-local. All the actions are computed pointwise, either in physical space or transform space. So it's very efficient. And I just want to finish by telling you a little bit of the theory about what we are developing, much of it led by Sam Lanthaler, to understand the benefits and drawbacks of these methods. And we have a review with Nick Kavatsky and Sam Lanthaler that will appear in the Handbook of Numerical Analysis, which has been the current volume, which will come out this year or next year. So the first theorem is this. Basically, it's a universal approximation theorem, but the key point is this, that in that setup I described to you, M only needs to be 1. So all I need to do is one integration. So this is about non-locality. All I need to do is integrate the function against a constant. So if those Fourier bases include a constant, it may not be a Fourier basis, but Fourier would include a constant. All I need to do is have one non-local operation, which is to compute the average. Then if the channel width is sufficiently large, and this is not stated very well, I apologize. For any epsilon, we can find a channel width to get the error between this Fourier neural operator and the truth to be as small as one likes. And so this is really remarkable. So you need conditions on continuity, and this is the supremum over a compact set. But within that class, you can approximate anything. And all you need is to be able to, in terms of non-locality, you just need to have computed one integral. It doesn't mean it's the most efficient to compute one integral, and I have things to say about that for anyone that's interested. But I think this is a beautiful theorem because it just shows the simplicity and what is needed to make universal approximation. But the second theorem is more negative and describes complexity. And again, this is not stated perfectly. I apologize, Overleaf has a problem for me, and normally I would have updated the slides, but I wasn't able to. That minus sign should not be here. Point of this is that the complexity of the approximation, which you can think of as being the number of parameters, can grow very badly, even across the class of operators which are CR, so that's R times continuously differentiable between the Banach spaces U and V. There are sequences of problems where to attain error epsilon, the cost grows like the exponential of C divided by epsilon to the B, C and B being positive. So the cost in terms of number of parameters, even for continuous functions with R continuous derivatives, grows exponentially in terms of the error. Now, there are lots of exceptions to this. And so, for example, in DeepONet, they've been shown for Darcy and hyperbolic conservation laws. For FNO, for Navier-Stokes equation, Sam has shown it for PCA in the Darcy case. And recently with Sam, we've looked at Hamilton-Jacobi equations. So on a case-by-case basis, you can replace this by algebraic growth. It's important to understand the whole of numerical PDEs is based on obtaining epsilon error with algebraic cost. This comes back to the question that I was asked earlier. But this is showing that these methods can be extremely bad, and that we're starting to understand classes of problems where they're not. And they include complicated conservation laws, Hamilton-Jacobi. But nonetheless, this is something where a lot more work is needed to understand when these methods might be more effective than standard numerical methods and when they might not be. But by the way, this question is not really answered for standard numerical methods either. It's just that we have many decades of experience and we know what is a good way of solving an elliptic problem or hyperbolic problem, Navier-Stokes equations, and so forth. Finally, my whole picture was to do everything in function space, but actually you have to enter reality at some point and do things in finite dimensions. The point of this final result is basically to do a numerical analysis, and this is with Margaret Troutner, who's an excellent PhD student in my group, which concerns the accuracy of the Fourier, what is essentially a pseudo-spectral approximation of the Fourier neural operator. I described it to you as if it acted on functions. In practice, you implement it with a pseudo-spectral method. The error between those decays like n to the minus s, where this is a grid of n to the d points, the dimension being d, and s is given by the regularity of the input hs. And I've assumed continuity of the mapping that we're learning. And we also, and this is an important practical point for implementation, we need the activation function to be CS as well to obtain this error. And we have numerical results that show that if you don't have this, for example, if you use ReLU, then with S bigger than 1, if you use ReLU, then you fail to achieve these rates of convergence. So there are important details here that interact with optimization and so forth, which is often done for practical reasons with ReLU. ReLU is not good enough for this. You really need to use smooth activation functions. I'm grateful to you all for listening. Here are the conclusions, but you can just read them. Thank you for all your questions and attention.
All the work that you've done, does it have to train on solutions to the numerical equation? The original numeric,
No.
Or some of the work I've seen, like George Karniadakis, the differential equations themselves are used as part of the objective function.
Yes, so I haven't done that, but there are people like Anima Anankuma, who is one of my collaborators in my department. She has done things which are in that direction, where one appends to the loss function something which has information about the equation itself. I do have a forthcoming paper with some collaborators in Cambridge where we're also doing the same thing in the context.
What's your feeling on what's a more promising direction?
I think my sense is that standard numerical methods are going to be more efficient in solving standard problems, and that eventually we'll end up with a theory that shows that. And that, however, for the reasons that I mentioned earlier, it may sometimes be expedient at relatively big, but still, accuracy that's not asymptotically small. It may be more efficient to use these methods. The reason I've concentrated here on just supervised learning is, and this I think is a direction which is perhaps has more promise. There are problems where we don't know the differential equation. So, for example, there are cyber physical systems where you have humans interacting with robot equipment. There are lots of experimental data about time continuous forcings that cause responses of human cyber physical systems and measurements of output. Of course, you can try and measure that. You can try and model that physically, but it's extremely complicated. It involves psychology and so forth, and how that interacts with a mechanical device. So we're starting to see systems where you will have, for example, time-dependent functions and loads of data. You don't have a model, and then this methodology can develop a model. So I think that's probably the most promising, but I think there will be uses in cases where we know the model as a PD. Thanks. Yes.
I think as we touched upon a little bit earlier, there's a input distribution that needed to be specified for some of these data models. And I'm curious, since a lot of these systems are physics-based, do we know that these kind of inputs, when randomly generated from a distribution, still satisfy these kind of physical constraints, and they actually make sense as inputs to the...
Yes. So we devote a lot of time to constructing probability measures with physically realistic inputs. If I go back to the Darcy problem, there are good physical scaling arguments for liking log normal input distributions. So those are functions which are computed as the exponential of the Gaussian random field. And so some of the work we've done for that, those problems uses log normality. There are also good physical examples, as I mentioned, of media where you change from, for example, sand to rock. So you can I'll combine the two things I'm saying in a moment, but at a coarse level, you can think of just two things, sand and rock. And then what matters is the interface between them. And one can model that through a random distribution. We do it with level sets of random functions, trying to be physically sensible in terms of what's known about the topology of those interface problems. And then I didn't do it here, but you can combine the two things I've said. So the sand itself will be log normal and the rock itself will be log normal. And so rather than having piecewise constant, you can do random interfaces with piecewise log normal functions. So all that is an example. More generally, to answer your question, it's very important to be physically realistic in the probability measures that put on the training data. And furthermore, there are questions about how efficient, what's the best set of data to use that's both physically reasonable and will, with the smallest amount of data, give you the best generalization model. So in plasticity, we've compared doing things like, there are lots of experiments done in plasticity in the past, physical experiments where people try and learn what are called constitutive laws from experiments where they load and unload and do various specific things periodically. Periodic in time loading and unloading, for example. We have looked at and compared doing those with random designs, which are much harder to do in the lab, but can be done in simulation studies. And we have empirical evidence of the benefits of being random, and we have we're starting to think about how to choose length, correlation times, and so forth in those processes. So this is a big area and very important. We're thinking about it, but there's much to be done. Thank you.
You touched a little bit on generalizability.
Yes.
You expand more on when this seems possible and when there's issues.
Yes. There are a lot of issues. I think many of these problems are difficult to generalize. And if I were to say that one of the things that's going to limit their ability to be used is this. We have very little theory about it. I'm going to the slides because I'm going to show you that in the linear case, we've developed some theory. And just to give you an idea of what is known theoretically, it only concerns the linear setting. And this is a very hard slide to take in, so I'll just point out at the high level what we study here. L and L dagger are linear operators, and this is it's called a Botman norm. It's a measure of the difference between L and L dagger, and we have rates of convergence. Key point is that these rates of convergence do involve generalization in that as part of the definition of this norm on the left, we work with probability measures that are different from the ones that we use to generate the data. Using this theory, which is hard to decode, we can quantify the degradation in the rate of convergence as a function here of the amount of data, and how that rate of convergence depends on how far the measure is used to compute the error here from the measure used to generate the data. So we have a quantitative estimate of the degradation in the accuracy as a function of data volume. In this very specific definition of generalization, where it's related to changing the regularity of the functions. So that's all that's known theoretically as far as I know about this question. In terms of empirical evidence, there is lots of evidence that it's limiting and that it's hard to go beyond where one wants, but there's also positive evidence. So I would say in fluid mechanics, the kind of problems which we're looking at, which are mildly turbulent, but not fully developed turbulence, the generalization is extremely poor. In the problems I've looked at in plasticity and viscoelasticity, empirically, it's very good. So that's somehow related to the complexity of those systems, but it's purely empirical. Thank you.
No more. Well, thank you very much, Henry.